Exploring Carbon Sequestration, Innovative Methods to Combat Climate Change. Introduction. Welcome to the first post in our series, Exploring Carbon Sequestration, a vital strategy in the fight against climate change. As we work to reduce emissions, we must also look at innovative ways to remove carbon dioxide, CO2, from the atmosphere and store it long-term. This post introduces a comprehensive list of 14 potential carbon sequestration methods, each evaluated for effectiveness, cost, scalability, and co-benefits. Let's dive in. What is carbon sequestration? Carbon sequestration involves capturing and storing atmospheric CO2, either by natural or engineered means. It's crucial to slowing the accumulation of greenhouse gases and mitigating global warming. Methodology: evaluating sequestration methods. We evaluated these methods based on 4 key criteria. Effectiveness: how much CO2 can the method capture or sequester? Cost: what are the financial implications of implementing this method at scale? Scalability: how easily can the method be scaled up globally? Co-benefits: does the method offer additional advantages, such as improving ecosystems or providing economic benefits? Each method was scored out of 40, with individual ratings for each category on a scale of 1 to 10. We also applied tie-breaking rules where needed, based on practicality and current readiness for large-scale implementation. Key sections: the top 14 carbon sequestration methods. 1. Carbon farming. Score: 32 out of 40. Carbon farming involves enhancing soil carbon sequestration through techniques like no-till farming, crop rotations, and cover cropping. This method is cost-effective, widely scalable, and brings numerous co-benefits, including improved soil health and biodiversity. 2. Farming underwater with seaweed. 32 out of 40. Seaweed farming captures CO2 through photosynthesis and can store it when sunk to deep ocean levels. Although highly effective, its scalability is still in development, with additional co-benefits such as restoring ocean habitats and biofuel potential. 3. Afforestation. Score: 31 out of 40. Afforestation involves planting new forests to absorb CO2. It's scalable and relatively low in cost, with significant ecological co-benefits like enhancing biodiversity and restoring ecosystems. 4. Reforestation. Score: 31 out of 40. This method focuses on restoring degraded forests. While it is equally effective, reforestation is geographically limited to areas that require forest restoration. 5. Coastal wetland restoration. Score: 30 out of 40. Restoring wetlands is one of the most effective carbon sequestration strategies. Wetlands store vast amounts of carbon and provide important co-benefits, such as flood protection, biodiversity enhancement, and supporting fisheries. 6. Biochar. Score: 29 out of 40. Biochar involves converting biomass into a charcoal-like substance that stores carbon in soil. This process enhances soil fertility, improves water retention in agricultural areas. 7. Urban greening. 29 out of 40. Urban greening increases vegetation in cities, absorbing CO2 while cooling urban areas and improving air quality. Although it has lower direct carbon sequestration potential, it offers significant urban co-benefits. 8. Bioenergy with carbon capture and storage. Score: 25 out of 40. BCS generates energy from biomass and captures the CO2 produced during combustion. This method offers negative emissions, though it's costly and requires significant infrastructure to scale. 9. Mineral carbonation. 24 out of 40. This process chemically reacts captured CO2 with minerals to form stable carbonate compounds. While it provides long-term stability, the process is expensive and limited by the availability of minerals. 10. Carbon capture and storage, CCS. Score: 24 out of 40. CCS captures CO2 from industrial sources and stores it underground. While highly effective, it's expensive and faces logistical challenges in scaling. 11. Enhanced weathering. 23 out of 40. This method accelerates the natural weathering of rocks like basalt to capture CO2. It's theoretically effective, but faces challenges in cost and scalability. 12. Direct air capture (AC). Score: 22 out of 40. DAC captures CO2 directly from the atmosphere using chemical processes. While highly effective, it's energy-intensive and costly. 13. Electrifying seas. 21 out of 40. This experimental method uses electricity to enhance natural oceanic processes for CO2 absorption. While promising, it's still in the research phase and comes with high costs and potential ecological risks. 14. Ocean fertilization, 18 out of 40. Ocean fertilization adds nutrients to stimulate phytoplankton growth, which absorbs CO2. Although cost-effective, this method is controversial due to potential ecological risks, such as harmful algal blooms. Summary of our research process. This list began with 12 methods, but after careful consideration, we added farming underwater with seaweed and electrifying seas to ensure a more comprehensive approach. We leveraged AI-based analysis to evaluate each method's effectiveness, cost, scalability, and co-benefits. The AI-assisted approach allowed us to efficiently cross-reference extensive datasets and research publications, generating a scoring system to rank these methods systematically. The top-ranking methods, such as carbon farming and farming underwater with seaweed, emerged as immediate considerations due to their high effectiveness and scalability.